if you carry out heat transfer calculations as part of your CFD analysis, then you may have come across a particular type of boundary condition called a convection boundary condition. And this boundary condition might appear a bit unusual to you because it's not the same as a fixed temperature boundary condition or a fixed heat flux boundary condition that you may be used to. So what I'm going to do in this video is I'm going to dive in and look specifically at convection boundary conditions. By the end of the talk, you're going to have a good idea of exactly what a convection boundary condition is, when you might apply it to your CFD codes, and what actually the different entries are that you need if you want to set up this particular boundary condition, including one particular entry, which is the heat transfer coefficient, which seems to be causing and creating a lot of confusion in the CFD community around this particular boundary condition. So if you carry out heat transfer and thermal modeling in your CFD calculations, this is going to be a great talk for you. Let's get into it. So today I'm going to be talking to you about what is a convection boundary condition, when should I use a convection boundary condition, and then at the end I'm just going to talk briefly about the difference between an internal heat transfer coefficient and an external heat transfer coefficient, because that's a common misconception that a number of people have with this boundary condition. And the way I'm going to describe a convection boundary condition to you in this talk is to just go through a simple example. And I found this simple example really helps to illustrate all of the concepts of a convection boundary condition so that you really understand it. And then you can just take the same example and apply it to your study as you see fit. And so the example I'm going to be going through today is just a very simple flow of a hot fluid along a pipe. And you can think of the hot fluid as hot water or any other hot fluid. And as you can see in the diagrams on the slide, we've got the hot fluid, say water, flowing horizontally along the pipe from left to right. And what you can see, of course, from the diagram is that we expect the velocity profile in that pipe to take the form of a parabolic profile or perhaps some other shape. And then surrounding the pipe, and this is the important part of this talk, the hot pipe is surrounded by air. So we've got a very simple flow scenario where we've got flow going along a pipe from left to right, and the pipe itself is surrounded by air. And as we go through, I'm just going to assume that the pipe wall is infinitely thin or a very good conductor. So we don't really need to think about that in this talk. And the idea for this flow scenario is that we want to calculate the velocity profile and the temperature distribution inside the pipe. So in this case, we're looking at a pipe, but you can think of this as any other internal flow geometry that you may have where you want to calculate your velocity and temperature profile inside some kind of region. And so the standard way that we do this in CFD is, of course, we create a computational mesh for the region that we're interested in. And so on the slide, you can see there, I've just given an example of a very simple structured grid that you could create for the inside of the pipe. And this is very straightforward, but the important question to ask at this stage is, what are the appropriate boundary conditions that we'd apply to the walls of the pipe or the walls of your internal flow geometry? Now it's reasonably straightforward. For the momentum boundary condition, most of you will of course realize that the appropriate boundary condition for momentum or velocity is the no slip condition at the wall. And so at the wall of the pipe, or on this red circle that I can show you in the diagram that surrounds the edge of the pipe, we apply a boundary condition of u equals 0 for momentum or velocity along the wall. But what about the thermal boundary condition or the temperature boundary condition? What boundary condition are we going to apply on the wall of the pipe in this case? Well, a good first guess to what the boundary condition might be would be to set the temperature of the pipe wall equal to the ambient air temperature that surrounds the pipe. So on a normal day, if your pipe was surrounded by air, we could quite easily assume that the wall of the pipe would be at 15 degrees Celsius, which is the temperature of the outside air. That would be a good first guess, but what I'm going to show you in this talk is that that boundary condition isn't quite correct, and we can actually do a lot better if we think carefully about the problem. And the reason that that fixed temperature boundary condition isn't quite correct is that the air around the pipe, of course, is going to be heated by the hot pipe. And what will happen as the air is heated is that, of course, the air rises and it will form a characteristic plume, or a region of hot air rising off the top of the pipe. And another way to think about this is that as the air is heated and it rises and moves around the pipe, it's going to be forming a very thin thermal boundary layer around the edge of the pipe, on the outside surface of the pipe. And because we have a boundary layer, if we were to plot the temperature along a line through that boundary layer, we may find that the temperature profile looks something like what you can see in the image on the left of the slide there. You'll get this fairly asymptotic temperature distribution, which far away from the pipe will have a value of 15 degrees C, the ambient air temperature. But then as we move along the line and get closer and closer to the wall of the pipe, of course the air is heated and so the temperature increases. So what you can see from that basic plot on the left is that actually the wall temperature of the pipe is actually hotter than 15 degrees C. So in this case we can see that it wouldn't actually be appropriate to apply a fixed temperature boundary condition of 15 degrees on the outer edge of our CFD mesh. We need to do a little bit better. And some of you, of course, when you look at this problem might think, yes, the simple way to address this is we've now got a flow outside the pipe as well. We can account for this in our CFD solver by meshing the air around the pipe as well. And you can see that there in the diagram. What I've done is I've just grown a mesh for the air volume around the pipe, and the air mesh is shown in blue there. And I've added a few inflation layers in there around the edge of the pipe. And with a mesh like this, if we give it to our CFD code, the CFD code will calculate the velocity and temperature distribution in the air around the pipe and also the hot fluid within the pipe. And this will allow us to capture the boundary layer on the outside surface of the pipe. And of course that face of the air mesh is linked to the face of the fluid inside the pipe. It's actually a two-sided or double-sided wall, and so the temperature of the wall will evolve naturally as part of the CFD solution process. It won't actually be a boundary condition that we apply. Now, this is one approach that we could take. If we have our internal flow geometry and we realize that the surrounding walls are going to be hot and heat the surrounding air, we could mesh the air around our internal flow geometry, and that would allow us to get the right solution. And if you do decide to take this approach, which you can do, of course, one thing you need to do is you need to make sure that the boundaries of this mesh for the air are sufficiently far away from the pipe cylinder or the internal flow geometry, as the extent of the boundaries can affect the flow structures that are developed on the surface of the pipe. And so often you'll see people maybe put the boundaries 10 pipe diameters or even 20 pipe diameters away from the pipe itself. And so what you can see straight away, that if you do take this approach of meshing the fluid around your hot surface, your hot CFD geometry, you can see that the CFD domain itself is very large. And this means that we'd end up having to add a lot of extra cells to our CFD mesh, and the calculation, of course, would be a lot slower. And there must be a better way we can address this problem. Is there any way we can get away with not meshing the air volume around our CFD geometry? And the other point to, of course, mention at this stage is that it's not only more cells. You don't just need to add more cells. You've now got a natural convection type calculation where the flow around the pipe is developing naturally. There's no forced flow, and these types of calculations can be difficult for CFD codes to converge. So not only have you got more cells, but you've now got a more difficult calculation. What can you do to avoid meshing the air around your CFD domain? Well, the trick is to use a convection boundary condition. And if we use a convection boundary condition, we go right back to the original problem where we only have to mesh the flow, that hot flow moving along the pipe inside our CFD domain, and we just apply the convection boundary to the external walls that are in contact with the air or the surrounding fluid. And with this approach, we don't have to mesh that surrounding fluid, so our calculation is probably going to be more stable and a lot quicker to run because our cell count is a lot lower. So the big question of this talk is, how does it work? How does a convection boundary condition work? it needs to in some way replicate those flow structures that would be developed on the outside surface of the pipe if we were to mesh them. And the trick with a convection boundary condition is what the CFD code will do is it will apply a heat flux boundary to the outside surface of that pipe that we selected. So we're not applying a fixed temperature of 15 degrees anymore, we're actually applying a heat flux boundary condition. And the question is, how is that heat flux calculated? In some way it needs to be consistent and representative of those flow structures, the natural convection plume that we've got developing on the outside of our pipe. The way the CFD code does it is by using Newton's law of cooling. And just a quick reminder for you guys of what Newton's law of cooling is and how does it work. The way to think of Newton's law of cooling is if you have a hot surface, call it a hot plate or any type of geometry, then the heat flux given off that hot surface can be given by the equation you see there on the slide, which is the heat transfer coefficient. I've called that H with a subscript EXT, which I'll explain a bit later, multiplied by the temperature difference between the wall and the temperature far away from the surface, which I'm going to call T infinity here. And the reason this equation is useful, of course, is another way that we could calculate the heat flux would be to calculate the temperature gradient right at the wall, and that would be an application of Fourier's law. However, if we were to take that approach, we'd have to have some way of calculating the temperature gradient at the wall, which is quite difficult to do without a CFD mesh. And so Newton's law of cooling provides a convenient way that we can get around that by saying, no, the heat flux is just going to be equal to the heat transfer coefficient, H, multiplied by that overall temperature difference, which you see there between the wall and the free stream temperature. So the heat transfer coefficient for this case is a convenient way that we can get around calculating the gradient of that temperature profile on the outside surface of the pipe or the wall. So just a quick refresh, what the CFD code is doing when we apply a convection boundary condition is we're applying a heat flux to the outside surface of that pipe rather than a fixed temperature boundary condition. And the equation that the CFD code will use will look something like equation 1. And now what we need to do is just have a think about the various terms in that equation, where they're going to come from and how you might apply them. Well, the first obvious point that we need to mention is that T infinity is the air temperature far away from the pipe. That's if we took our line and we extended it far away from the pipe, we'd reach the ambient conditions. And for this case, we've said it's probably an air temperature of 15 degrees C. So the T infinity is something that the user will have to tell the CFD code, because as a reminder, the CFD code doesn't actually know what's going on around the pipe. We know that there is air and the air is at 15 degrees C, but the CFD code doesn't know that. So we tell the CFD code what the conditions are like by telling it the temperature, T infinity, far away from the pipe. And so for those of you who are running a simulation, of course, you could look at a 15 degrees C air temperature around the pipe, but what happens if you had a very hot day? If the air temperature was, say, 25 degrees or 30 degrees, the shape of that plume and the heat flux drawn off the pipe would be very different. So the CFD code has to have a way of knowing what's going on outside your CFD domain, and it does that through the T infinity. Now, T wall, that's going to be calculated as part of the CFD solution process. Most often it's taken as the temperature of the wall from the previous iteration, so that's something internal to the CFD code and we don't really need to worry about that. The only other thing we need to worry about is this external heat transfer coefficient, which I've called H with a subscript of EXT. How do we get this heat transfer coefficient and what does it mean? Because we need to tell the CFD code what the external heat transfer coefficient is, so we have to have some way of figuring it out. And in this context, what I find really useful and helpful for understanding what the convection boundary condition is doing is that the external heat transfer coefficient is telling us what the conditions are like outside the pipe, or how effective the heat transfer is. And I've got two very simple examples for you on the slide just to help really crystallize this for you. Let's say your pipe is surrounded by air at 15 degrees C. Now that would have your T infinity would be the same in both cases, but under one condition, what happens if that air is being blown over the pipe by a gust of wind, say a very windy day? But what would also be the case if there was very little wind, if it was a very quiet day? Clearly those two cases would be very different, and they'd affect the shape of the plume that grows off that pipe and how much heat is actually drawn off the pipe by the wind. Because of course we would expect on a windy day that a lot more heat will be drawn off the pipe by the wind. And so we have to have some method of telling the CFD code what the conditions are like outside the pipe and how effective the heat transfer coefficient is. And so the way we do that is through the heat transfer coefficient, HEXT in this case. And the way to think of it when you're putting in a value, of course, is that a larger value of H tells the CFD code that the heat transfer outside the pipe is more effective and more heat is going to be drawn off the pipe. So if it's a windy day, you're going to expect H to be larger than if it's on a very quiet day. And this is just a recap of what we talked about on the previous slide, just a reminder and to really hammer home that the CFD code has no idea what's happening outside of the pipe. If we were to mesh the air around the pipe, then the CFD code would know, because it would develop the boundary layer and calculate the velocity and the temperature. But with a convection boundary condition, it has no idea, and so we have to tell it what's going on outside the pipe. Now we've got a good understanding of what this external heat transfer coefficient actually means. The next question is, how do we calculate it? Because we have to give the CFD code a value. Now, the trick with the external heat transfer coefficient is you're going to need to find an empirical correlation or a set of experimental data or a simplified CFD model to provide a value of the external heat transfer coefficient. And in most cases, you can get these correlations for the heat transfer coefficient from heat transfer textbooks. And I'll have one particular heat transfer textbook linked in the description that has a number of these correlations which you can use. And if you search for a heat transfer correlation, say for in this case you've got a natural convection plume developing off a pipe or a circular cylinder, what you'll find is that many of these correlations are presented in the form of a Nusselt number. And at this point it's easy to get lost and confused, and that's why I really wanted to just remind everyone the Nusselt number, what it actually represents is it's just the dimensionless form of the heat transfer coefficient. So no need to get confused or lost when you're looking up a correlation to apply for one of these heat transfer coefficients. You'll often actually just need to look up the Nusselt number, which is the dimensionless form. It has no units. And you may find that the correlation looks something like the sketch that I've got for you there on the slide, where on the x-axis you've got the ambient conditions expressed in some form, which I'm going to go through in a bit, but on the y-axis you can see we've got the Nusselt number, which is the external heat transfer coefficient multiplied by the pipe diameter and divided by the conductivity of the air. So you can see it straight away that if you had access to a plot like this that you can see on the screen, what you would do is you'd select the ambient conditions that you had on the x-axis, and then you would just read up to the line or the data and then read off the Nusselt number, which you could then use that formula to rearrange for the heat transfer coefficient, and that's what you'd give to your CFD code. So hopefully on this slide you've got a good idea of roughly how the process works and a good understanding. What I'm going to do now to help you guys out is to just give you a quick example with some numbers to really help crystallize what we're talking about here. And the example I'm going to use is very straightforward. We're still using the same pipe geometry that we were considering before, but I'm going to consider the case where we've got a wind blowing outside the pipe at 2 meters per second. So we've got a 2 meter per second wind blowing past the pipe, and the pipe has a diameter of 0.5 meter. So it's a fairly big pipe that you may have outside in a factory or warehouse setting, for example. And the first thing we do in this situation is we calculate the Reynolds number. And of course, many of you will have guessed that the Reynolds number is an excellent way of representing the ambient conditions or what's going on to the flow outside the pipe. And so that's exactly what we do here. We calculate the Reynolds number for the wind, and in this case we find it's about 62,000. And then what we do is we go to our heat transfer textbook and carefully choose the right correlation. And I really want to emphasize carefully here, because of course every flow scenario is going to be different, and if you're not looking at the pipe, if you're looking at something else in your calculation, then the correlations that I'm using here aren't going to be appropriate and you'll get the wrong answer. So you really need to be careful in the correlations that you choose and have a good read of the textbooks, and perhaps get a colleague or someone to check after you've done the work that you've selected the right one. But for pipe flow with forced flow over I'm going to choose a correlation for forced flow over a circle or a circular cylinder, and I'm using the heat transfer book, Fundamentals of Heat and Mass Transfer 6th edition, which is linked in the description if you want to see that particular book. And the correlation that I've chosen, you can see, is there in equation 3. And for the circular cylinder that we're looking at here, you can see that the Nusselt number is 0.027 multiplied by the Reynolds number to a power, and then multiplied by the molecular Prandtl number to the power 1/3. So looking in that formula straight away, equation 3, you can see that the Reynolds number is really representing the ambient conditions. So outside of your CFD domain, what's happening with the ambient conditions? In this case, you've got some wind. You've got wind at some velocity, and that's captured through the Reynolds number. And just as a reminder, the molecular Prandtl number is just a material property of the fluid. In this case, for air, it takes about a value of around about 0.7. So there's not really any need to worry about the molecular Prandtl number for this correlation. So you can see there, equation 3, we calculate the Nusselt number using our correlation, which has a value of 177, and it's dimensionless, so it has no units. And then what we do is we take that formula from before and we rearrange it to calculate the external heat transfer coefficient. And in this case, the external heat transfer coefficient has a value of 9 watts per meter squared Kelvin. So this is it. This is our solution. This is what we can apply back to our CFD code. And so if we now think about what we've done and bring everything together, we've got our pipe flow and we've got hot fluid going along the pipe, and we've generated a mesh for the pipe, and we're going to use a convection boundary condition on the outside surface. So instead of applying a fixed temperature, we tell the CFD code the free stream temperature far away from the pipe, and then we also tell it the external heat transfer coefficient so that the CFD code knows what kind of conditions are happening outside of the pipe, so that the CFD code can apply the right heat flux to your domain. And of course, the final point to emphasize from this slide, of course, is that there's no mesh for the air. We're only meshing the flow on the inside of our pipe. And what I wanted to do now is just quickly point out where some of the input options are for ANSYS Fluent users, because I know many of you are ANSYS users and you'll want confirmation of where these values are actually applied. So if you were to create this pipe geometry and load it into ANSYS Fluent, when you select the boundary condition for the external surface of the pipe, if you go to the thermal tab in the boundary conditions where you enter it, you'll notice under thermal conditions you have a choice of heat flux, temperature, or convection. And what we've been talking about today is convection. So of course you select the convection option, and then you'll notice that there are 2 boxes there where you can enter the external heat transfer coefficient, which we derived earlier, took a value of 9.2, and the free stream temperature. So this way the CFD code knows what the conditions are like outside of the pipe. Now, if you're an ANSYS CFX user or another CFD code and you select a convection boundary condition, you'll also find these 2 entries that you need to fill in for the free stream temperature and the external heat transfer coefficient. Now, OpenFOAM users, I know I have a few OpenFOAM users watching the videos, and for you guys, the boundary condition you're looking for is the external wall heat flux temperature boundary condition. And this boundary condition has several different modes available to it, and you want to select the coefficient mode, and that tells OpenFOAM that you're applying the external heat flux as a heat transfer coefficient. And what I've got for you there on the screen is just a little segment of code that you may use if you're an OpenFOAM user, and straight away you can see there that under mode we've got coefficient to tell OpenFOAM I want to apply this heat flux as an external heat transfer coefficient. And then you've got TA and H. In this case, TA is the ambient temperature of 15 degrees C, which we've converted to Kelvin by adding 273.15. And then under H, we've got that heat transfer coefficient that we derived earlier. Now, Before going on, it's worth pointing out that those few calculations that we did earlier for the heat transfer coefficient and the Nusselt number, that's something that it's probably worth doing. You can sometimes do that within the CFD code if you have some kind of coding interface for your CFD code of choice, but often it's easier just to work out those few equations in Excel or MATLAB or Python yourself. It usually only takes a few lines, but it's worthwhile doing so that you can quickly change the numbers if you decide that your wind speed changes, for example. It's a very quick and easy way to do things. Now, before wrapping up, I just want to make note of a few more points which will really help bring home the talk and everything we've talked about today. And the first thing I want to do is just to talk about applications. And the reason I want to talk about applications is because as a CFD user yourself, you may come across a variety of different CFD simulations, and it's useful to recognize and realize when you need to use a convection boundary condition, because you may be given a new case that you're not used to before, and you'll want to identify straight away, this is a case where I can use a convection boundary condition and I don't have to mesh a large volume of fluid. And just some typical examples where convection boundary conditions tend to show up are problems like buildings. So if you're looking at the flow and temperature inside a building with some hot components or hot rooms, maybe you're looking at a ventilation system, then the roof and the walls of that building are going to be exposed to ambient air. And as a CFD user, you don't really want to have to mesh all of the air surrounding your building unless you have to. And so convection boundary conditions often appear for building roofs and walls. Likewise, if you have chimneys in factories, power stations and warehouses, large chimneys, that the long cylindrical surface of the chimney, of course, is going to be exposed to the ambient air, and so you may want to use a convection boundary condition there. And then the final application that I thought of was open water. So if you open water or a water tank, for example, if you have an object in a water tank or out in an external flow environment, then the outside surface, rather than having to mesh the surrounding sea, river, or perhaps water tank, that's a place where you could also try and apply a convection boundary condition. So the trick with all of these, of course, and you may notice this in your model as well, is to think about when would I need to mesh a large volume of fluid outside my domain. And in the example that I've got for you here, I've just got a building wall in the left plot. I've got a building wall, and then the red line shows where the wall is. And then in this case, of course, I'd have to mesh all of the air outside the building so that I could capture that thermal boundary layer that would be developing on the outside of the wall. But in this case, of course, what we can do is just get rid of the outside air and replace it with a convection boundary condition, and make sure that we choose a careful correlation to calculate the effect of that thermal boundary layer that would be driven up the outside wall there. And finally, just to finish off, what I want to do is just go through a common misconception that many people have, and I'm sure this will clear up a lot of things for you if you're a user of these types of models. The thing to notice is that with the convection boundary condition, we've been focusing on the boundary layer on the outside surface of our domain. But it's important to also recognize that we've also got a thermal boundary layer on the inside surface of the pipe. And you can see that there on the diagram. I've just highlighted it for you. We've also got a thermal boundary layer on the inside surface of our pipe. And so really there are going to be two types of heat transfer coefficients. And this is actually where a lot of the confusion comes in and where people have a lot of difficulty setting up their CFD codes. And what I want you to think about in this case is that what we've done is we've meshed the inside of our pipe. So we've meshed the inside of our pipe and we've applied a convection boundary condition on the outside. And because we've meshed the inside of our pipe, what that means is that the CFD code is going to be calculating the flow and temperature distribution inside the pipe. And so the CFD code is going to be calculating the boundary layer directly for us on the inside of the pipe. And what that means is that the heat transfer coefficient on the inside of the pipe is not something that we apply as an input to the CFD code. The heat transfer coefficient on the inside of the pipe is something that we can get out of the CFD code as a result or an output. And if you're interested for details about how you would do that, how perhaps you would mesh the inside of the pipe and extract a heat transfer coefficient from that calculation, you can see my previous video on heat transfer coefficient, and that goes through in detail how you might do this with different CFD codes. But the key takeaway message from this talk, and something that I really want you to understand, is that the external heat transfer coefficient is an input to the calculation. We need to tell the CFD code what the heat transfer coefficient is on the outside of the pipe, because that's where we don't have a mesh. But the internal heat transfer coefficient is something that we get as an output from the CFD calculation, because that's where we have a mesh, that's where we calculate the thermal boundary layer, and that's where we do our post-processing to calculate the internal heat transfer coefficient. So hopefully this little description at the end just helps you to sort out for your case, what heat transfer coefficients am I going to be getting as outputs to my calculation, and which bits do I have to apply as inputs? I'm really hoping at the end of this talk that you'll be crystal clear about which ones you're applying and which ones you're solving in your CFD simulation. So just a summary to wrap up what we've talked about today. A convection boundary condition is a type of thermal boundary condition that we can apply in a CFD model. It's an alternative to a fixed temperature or a fixed heat flux boundary condition. And the reason that we use it is we use it to model the boundary layer and the flow on the outside of the CFD model that we're not including directly in our mesh. And by applying this boundary condition, we mean we don't have to mesh the outside of our domain, so we save a lot of cells, and so our computational time is going to be a lot quicker. It's going to have a lot quicker simulation, and it's also likely to be more stable converging, because we don't have to do a natural convection calculation, which can be difficult to converge for some CFD solvers. And as far as an action point for you from watching this talk, what you may have noticed is that the external heat transfer coefficient is something that you need to calculate yourself and apply it to the CFD domain. And you can get these values from experimental data, or what I've shown you here is how to use an empirical correlation to do it, or you can use a sectional model instead. You could actually develop a separate CFD calculation for the outside of your domain if you wanted. But the external heat transfer coefficient is something that you apply to your CFD model, and this is in contrast to the internal heat transfer coefficient, which is something that you'd get out as part of the solution to your CFD calculation. So that brings me to the end of the talk. I put together this talk after the success of my last video on the heat transfer coefficient, as many of you seem to like this new format where I'd go through some of the theory behind a particular boundary condition or process, and then show you exactly what entries you'd have to fill in various CFD codes like ANSYS Fluent or OpenFOAM. Many of you seem to really like that and knowing exactly what entries to put into which boxes and what they mean. So let me know in the comment section to this video, did you like the similar format? Is this something you'd like to see more of? Because I'm considering looking at some of the other boundary conditions as well. And if I know that this is helping a lot of people out and you're finding it really useful knowing what the different boundary conditions are and actually what the different entries mean in the CFD code, then let me know, and I'll try and consider prioritizing those videos for the future. And I also hope with this video that I've managed to clear up some of the misconceptions that some people seem to have around heat transfer coefficients, especially as there are some instances where you think I might need to apply a heat transfer coefficient to a CFD model, and there are other instances where you might actually get that as an output to a CFD model. So let me know again if that's been particularly helpful for you. I really do enjoy hearing from you and listening to all your feedback. It really does help me to plan my future videos. So until next time, thank you all very much for watching. I appreciate it, and I'll see you next time.